Welcome to the Galactic Embers Podcast, where we unravel the mysteries of the universe for those who have a scientific bent of mind but don't necessarily have training in the field of astronomy or astrophysics. I'm your host, Sarv Parteek Singh, and I'm an engineer who is currently pursuing a graduate degree in applied physics at Johns Hopkins University. Our guest for today is Dr. Eddie Schlafly. Dr. Schlafly is an associate astronomer at NASA's Space Telescope Science Institute, where he's trying to understand the structure of the galaxy, especially its dust, using observations of stars. He leads the processing pipeline for the Nancy Grace Roman Space Telescope and is the survey coordinator for Dark Energy Spectroscopic Instrument. His recent work uses certain instruments to measure the properties of billions of stars as part of understanding the galaxy's stars, gas, and dust. He also uses spectroscopy to understand how dust properties vary and is working on inferring the three dimensional structure of dust in the Milky Way galaxy. Dr. Schlafly has a stellar, pun intended, academic history. He did his bachelor's from Stanford and PhD from Harvard, both in physics. After that, he had research and academic appointments at the Max Planck Institute for Astronomy in Germany, Lawrence Berkeley National Lab, Lawrence Livermore National Lab, Space Telescope Science Institute, and the Johns Hopkins University, all in the US. Now, I've been fortunate to have Dr. Schlafly as my research advisor for the past few months, and I'm very excited to present this podcast with him where we talk about the secrets of stars. Now, fortunately or unfortunately, stars are not the only things I learned about in this podcast. I also learned that on the day of this podcast, my internet connection was spotty, which means that you would see my video lagging behind or being of lower quality than Dr. Schlafly's. The bigger problem was that there were some audio gaps, which I have gone ahead and fixed, so there should be no problem in your listening experience. I hope you enjoy this podcast.
Welcome, Dr. Schlafly. So today we want to talk about basically giving an introduction to people about, stars and what we mean when we talk about starlight, star parameters, and similar stuff. So the first thing is when you look up at the night sky, which I guess everyone has done since their childhood. What exactly are we seeing? Like, how many stars are there in the sky? Because, well, one popular thing people would say is that you can never count how many stars there are in the sky and how many hairs you have on your head. So as an astronomer, could you tell us a little bit more about whether we have answers to these questions?
Yeah, I can try to answer that. Yeah. So what do you see in the sky? If it's day, you see the sun and a blue sky and very little else. And then if it's night, you see a heck of a lot of stars. It depends on where you are. If you're somewhere dark, you see a lot of stars. And if you have really, really good eyes, maybe you see one galaxy, the Andromeda galaxy, if you're somewhere very dark, and the moon. You see the moon, and there and some planets. And I think that's about all that you can see if you just look up at the sky with your eyes. And those are all very different things. So the moon obviously is a giant rock like the Earth in some sense that's quite near the Earth, and then the planets are further away, but still close on astronomical scales. The stars are other objects like the sun that are very bright. They're emitting their own light. And can be the standard distances in astronomy is the parsec, which is 3 light years, so that the distance that light travels in a year. And so typical stars that you see will be on the order of hundreds of parsecs or a kiloparsec away, so thousands of light years. Whereas like the sun is 8 light minutes away, so that a minute versus thousands of years of light travel time. And then the nearest galaxy, the Andromeda galaxy, which again you can barely see if you have very good eyes and are in a dark site, is almost 1 million light years away. 1 million parsecs away, so 3 million light years away. So that's everything that there is that's up there to see and look at. So how many objects are there? It's a lot. So the Milky Way galaxy, is the galaxy that we live in. So all the stars that we see are in the Milky Way. And there's the mass of the Milky Way is like a trillion solar masses. So there's sort of enough mass to make a trillion stars. But all of the mass of the Milky Way is not in the form of stars. There's other stuff in our galaxy like dark matter, like gas, and like dust. And I actually don't know the number of stars that we expect in the Milky Way, but it's on the order of 100 billion, so something like 10% of the total mass, on that order.
I see. So these are 100 billion stars in the Milky Way galaxy, but then you look up the sky. You said that we could look at other galaxies, would also have somewhere on the order of that number of stars.
Yeah, so the Andromeda galaxy that I mentioned earlier is usually thought to be somewhat more massive than the Milky Way, and so it have more stars, but the same order of magnitude. And that's just one galaxy. That's the only one that you can see with your eyes. But it's definitely not the only other galaxy out there. And so if you have much better eyes than the average person, and you start looking at a patch of the sky very carefully, most of the objects that you see are not stars anymore, but they're galaxies that are quite far away. And so, yeah, the number of galaxies in the universe is very large. That number I don't actually have any clue for, and it gets into questions of like how big is the universe, and there's the observable universe that we can see that light has had time to reach us from, but then we shouldn't. It would be crazy to assume that the observable universe is the whole universe. So I think the right answer to the question of how many galaxies there are is infinity.
Right, and so maybe for the audience, you could talk a little bit about when you say the observable universe. Why is it that the whole universe is bigger than the observable universe? Maybe you could talk a little bit about how the universe is expanding, and just a brief nugget of that, because I do have a lot of questions from the interesting tidbits that you've given.
Yeah, that gets detailed. There's a famous paradox though called Olber's paradox, which is maybe interesting there. So Olber's paradox is if you pretended that the universe were infinite, and like the density of stars in the universe were constant. So any patch of the universe were equally likely to have a star in it. And you like pointed in any direction of the sky, you would conclude that eventually in that direction you would hit a star. And so then Olber's paradox is why is the night sky dark? Why, if every direction I point in eventually hits a star, why isn't the entire sky white with starlight instead of dark? And it that turns out to be a very deep and important question, and gets into this question of like the observable universe is finite. So the Big Bang went off and has like very, very rapidly expanded the universe, and such that when we look back, when we look at faraway things, we see things as they were when the light that they emitted was emitted. So if you look back if you look back at an object that's a gigaparsec away, a billion light years away, you're seeing that object as it looked a billion years ago. And if you go far enough back in time, there aren't any stars anymore. The stars haven't formed, and if you keep going back in time before that, there aren't any galaxies, there aren't any objects, and there's just a sea of gas. And so that kind of answers Olber's paradox, that if you look very far away, there aren't any stars anymore. You're looking at a time in the universe when there weren't stars. It was just objects hadn't conglomerated enough, gravity hadn't pulled things together enough, and you don't have any objects in the universe at that time. And it is true that if you look back at any point in the sky, eventually, like if you have a very old television that has an antenna on it, and you look at some of the static on the television where there isn't a channel, I can't remember the fraction, but something like 10% of the static, not terribly tiny fraction of the static is leftover light from what's called the cosmic microwave background, but it's from the very early universe when all of the universe was an ionized gas and emitting light. And so you do see like the beginnings of the universe in all directions if you look at the right wavelengths, but it's not very interesting. It looks like static on your television.
Yeah, sounds good. Thank you. So now we were talking about stars, and you've mentioned that in few cases, well, if you have a clear enough patch of sky, you could observe certain sections of this of say the Andromeda galaxy, or there are certain stars that are more visible than the other, and people over centuries have given them different kinds of names, like the brightest star,
or stars which come together to form a constellation. But
so we do know that not all stars are alike. There's a difference between different stars. So could you tell us a little bit about why some stars are brighter than others? Is it just about distance, or is there more to it?
Yeah, exactly. So there's some things that make stars look different depending on where they are. So as you say, so distance is one thing. The sun looks different than other stars because it is so very close to us. There's other environmental differences of stars, meaning there's this stuff called dust in the universe that is kind of like smoke. And if you look at a star that's behind a lot of dust, or it looks different. So that just like if you look outside and there's a lot of smoke in a particular direction, you look at something behind the smoke, it'll look smoky. And that's not because the object itself is smoky, it's because there's smoke between you and that object. And so there's some kind of environmental differences that make stars look different from one another, where they are, what's between you and them. And then the other thing that makes stars look different from one another is things that are sort of intrinsic to the star. And the most important of those is mass. So the mass of a star determines how it looks. And so some stars are very big and massive, and other stars started life with just a small amount of gas, and so look quite different than their more massive brethren. And sort of unsurprisingly, a very massive star is brighter than a very light star. So I'm trying to think of what like the famous supermassive stars are that people know the names of. Like I think Sirius is an O or a B star, which are quite young, massive stars. Betelgeuse, in my memory, is a red giant. Is another quite massive star. So some of the stars that people know by names are these massive stars that look different because they legitimately are quite massive. And then other stars are sort of normal, like Alpha Centauri is, famously the nearest star to the Earth that isn't the sun. It's a quite normal star. So anyway, the mass is the most important thing that sets, what makes one star look different from another. The next thing that people talk about is the age of a star. So if the star just formed from a big pile of gas, and is very young, it looks different than an old star. If you wait long enough, like the star will explode as a supernova, and obviously that makes it look very, very different. So you've got the age, and then the last thing you've got is what the star is made of. That's kind of the least important, because most stars are made of basically the same stuff, meaning it's a giant pile of hydrogen gas, some helium gas, not very much else. But there is an admixture, so when stars burn, they burn hydrogen and helium into heavier elements, carbon, nitrogen, oxygen, iron. Iron actually is formed in like supernovas when they explode, but ultimately the stars make this stuff, and they spray it back out into the space between the stars, and then later stars form out of that gas that's been polluted by these explosions or smoke produced by the earlier generations of stars. And so if you look carefully at a star, you can see that this star has a little more iron than that star. And that's sort of the last thing that makes one star look different from another. Those are the big factors that make stars look different.
So thank you for that. And then you mentioned that there's this smoke. Is this, so for the audience, could you enlighten us on how is this smoke different from the smoke in the space? Is it the same or is it different? And what do we mean by that smoke or dust?
I talk about dust as dust in the Milky Way galaxy as being similar to smoke because in many ways it is similar, and so both smoke on the Earth and smoke in space from stars, dust are sort of produced by a burning process. So it's not the same burning process. You've got a chemical burning going on in a fireplace on the Earth, and you've got a fusion burning process going on in the center of the star. But there's some kind of process that happens that turns one material into another material and produces a lot of energy, and then produces also these small particles. And so your smoke in your fireplace is lots of small particles of black material, where small can be quite small. I think in both the cases of soot on Earth and dust in the galaxy, typical sizes might be 10 nanometers, 100 nanometers. It'll be starting to get quite large. In both cases, so you're producing these small bits of material, so small grains of dust, both on the ground and in space, and it's the presence of those large numbers of small grains that makes smoke on Earth look like it does, and make dust in space look like it does. So that's it's those small grains that are scattering light out. When you try to look through them, you're not seeing everything that's behind them. You're seeing a bunch of white that is just the ambient light that's being scattered into your line of sight. And in the same way, if you look at the place that you primarily see in the Milky Way galaxy dust is if you are in a dark location and you look up at the sky and you see the Milky Way, you see the sort of white glow, white stripe through the sky. And then you look at that stripe carefully, you notice that it has some black blobs going through it. It's those black blobs that's not that the stars are shaped that way. It's that there's a bunch of dust in that location that's preventing you from seeing the starlight behind it. So those are the ways that dust and smoke on Earth are similar. They're not in detail. They're not the same. Smoke on Earth is mostly carbon and oxygen. It's actually not that different. In space, it's also mostly so-called carbonaceous grains. So carbon and oxygen are quite typical. There's a lot more silicate dust in space. So that the chemical compositions are not going to be that similar. Certainly, as you go detailed, how grains form in space is the conditions are close to a vacuum. The densities are very different. So the detailed compositions are going to be quite different, but surprisingly similar effects.
Right, and then to observe these things in detail in space, when we're talking about starlight, we have been using telescopes for centuries, right? So early humans were observing them with the naked eye, and then since Galileo, we started observing them in telescopes. So you work at NASA's Space Telescope Science Institute.
Could you tell us a little bit about how a telescope works?
or why we even need a space telescope.
Yeah, sure. I can talk a little bit about telescopes. I mean, very broadly, the thing that a telescope buys you is that it's bigger than your eye. So when you look at something, you're collecting photons that are, in most cases, the star has made the light, so it's made a photon, and that photon has traveled uninterrupted for the last, we'll say 1,000 years, 10,000 years, and it has then hit the lens in your eye and been focused onto your retina and records a little pulse in your retina. So it's kind of amazing. Like when you look at a star, that photon has just spent its entire life, the 10,000 years or whatever, going in a straight line right to your eye until finally being registered as a little blip in your retina. And your retina, will record all the light that it sees, but it's got to go through that little lens in your eye. So the big thing a telescope buys you is you can make that lens a lot bigger, and so you can collect a lot more light. So that's number one. Number two is that you can put better detectors in a telescope than you can make for your eye. So the eye is sensitive to a pretty narrow range of wavelengths. I should know what that range of wavelengths is, but I'm not actually sure. But on the order of 500 to 700 nanometers, and with quantum efficiencies, with sensitivities that are not 100%. So some photons will be missed when they enter your eye. But modern detectors, we're sensitive to a huge range of wavelengths. Typical, CCDs that you put in a camera, or the so-called CMOS devices that go into something, or the Mercator devices that go into something like the Roman Space Telescope, are sensitive all the way from say 300 or 400 nanometers out to 2 microns. So a very wide range of wavelengths of light. So in wavelength of light, that's basically the color of a light. And so the blue end of what you see is sort of 400, 500 nanometers. The red end of what you see is sort of like 700 nanometers. And so everything blueward of 400 nanometers, so smaller wavelengths, you don't see with your eyes, but that's that I guess we would call ultraviolet. And then redward is we would call sort of infrared. But there's a lot of light that comes out there, and you can learn from it. And so with better detectors, you get more light and sensitive to a wider range of wavelengths. So that's sort of what a telescope does. It gives you a bigger aperture to collect more light, and more sensitive detectors to collect more wavelengths and learn more about the wavelengths that you see. The other big thing that a telescope does is what's called resolution. So what's kind of like the smallest thing that you can see. When people talk about like a spy satellite being able to read the text on the newspaper in some other country from space, like that's saying it has a lot of resolution to be able to make out the little tiny letters. And so there's something called the diffraction limit. So the bigger the mirror that you make, if you get everything perfect, that lets you resolve finer details. And so if you make the mirror twice as big, you can observe details that are twice as small. And so there's a big effort to make bigger and bigger mirrors so that you can resolve smaller and smaller features. The sort of perhaps the number one driver of that particular technology today is observing exoplanets. So if you want to see a planet in orbit a star, that's not like Mars around the sun. If you want it to be any other star, that planet and that star are really close to one another, and and so you've got to have a really big telescope with a big mirror to be able to pick out that very fine detail.
And so that gives us an idea of why we should be using telescopes. Could you talk a little bit about why we want to have these telescopes in space as compared to on the ground?
Yeah, space does bring several important advantages. So one, so on this resolution side of things, when you look at an image through the atmosphere blurs it, and so like to give an extreme case that people are probably familiar with, sometimes you're driving on the road and it's a really hot day, and you see these mirage effects where you can like literally see the air, above the road like shaking, and sometimes you can even see the sky reflected through the air above the road due to how the index of refraction in the air is changing as it gets really hot. That's sort of an extreme example, but the point is the air that the light is going through affects like how the light travels and blurs it out. And so sort of everywhere you look through the atmosphere, you're looking at it through a kind of frosted shower glass that makes it hard to see. And so if you take your telescope up into space, you no longer have to look through this frosted shower glass, and everything looks much clearer. That's not the full story. There are lots of technologies on the ground to try to improve the resolution that you can get and to take out this frosted shower glass effect. So these are known as adaptive optics. So there's a huge amount of work there. But if you could, you would just put all your telescopes in space, and you wouldn't have to deal with it, and it would be wonderful. And so that's one huge benefit that going to space buys you. The other huge benefit that going to space buys you is the fact that the atmosphere isn't transparent. So, unsurprisingly, our eyes work at wavelengths where the atmosphere is transparent. If we, open our eyes and look at something, we don't just see the air. We see, stuff that's through the air, and if there's a lot of smoke, then it's hard to see. But if our eyes worked at different frequencies, then we would not see anything. We would, really only see the air. It would be like, being in a steam room all the time, and you just see fog. And so so if you go blue in the ultraviolet too far, the atmosphere starts becoming, not transparent at all. And so like the Hubble Space Telescope has a ton of capabilities that operate in the ultraviolet, because you just cannot do those wavelengths from the ground. And likewise, as you go into the infrared too far, I'm forgetting where the big water bands are that make it impossible to see any distance through the atmosphere at those wavelengths. But like around 1.1 microns or so, there's a huge dip in the transparency of the atmosphere where you just can't see through anymore. And if you want to look at any objects at those frequencies, you need to go to space. You need to get away from the atmosphere.
I see. And so would it be possible for you to share some of the things that you, as an astronomer, could look at from your telescopes, which, is different from what I could see when I just go out at my terrace and look at the night sky? Are there images that maybe you could share and other people could look at?
Yeah, let me share my my screen. The group I work with does a lot of big surveys of the night sky, and I think they're super cool. So this is an image of the sky. So this is just a website, anyone can go to it. So legacysurvey.org/viewer that has a compilation of a large number of sky surveys, and so this is the sky as seen by a particular instrument. So this is the WISE satellite observing the sky in the near infrared, so wavelengths that are hard to see from the ground.
So this is a space telescope.
This is a space telescope. That's right. So WISE is a satellite.
If you could give us a little bit idea of like what this wave is and what these dots represent.
Yep, absolutely. Right. So this is an image of the sky from WISE. This satellite that's been observing the sky in the near infrared. Actually just finished its mission, but it was observing the sky for more than 10 years. And so this is kind of what the sky looks like at some wavelengths. The most prominent thing that you see here is this this weird wave structure. So this is partially a projection effect. Whenever whenever you make a map of something that's a sphere like the Earth or the sky, there's sort of weird effects. This is really kind of a straight line in the sky, but it's kind of looks weird because of the Mercator projection and that kind of thing. But so this is a straight line through the sky. This is the Milky Way. So if you are on a very dark side and look up and see a white line through the sky, it's the Milky Way. It's this white line. It's there because this is where most of the stars in the Milky Way galaxy are. The Milky Way galaxy is this sort of flat disk, and we are in this flat disk. And so there's when you're looking through the disk, you see tons of stars. That's where the Milky Way. That's where this line is. When you're looking outside of the disk, you do see very few stars. That's where the things are relatively dark. There's a couple of objects down here, and this these are the same objects. This is repeated. So the sky is a sphere, and so if you keep going to one side, you're basically just going around the sphere again and again. But these two objects here are what are known as the Magellanic Clouds, so two very nearby dwarf galaxies to the Milky Way. I talked a little bit earlier about the Andromeda galaxy, which it's got to be this galaxy here. I hope. So it's this is, you can kind of see this disk structure, and this is a galaxy just like the Milky Way, but one that we're looking at from outside of the Milky Way. And so all this light that you see is just huge numbers of stars in Andromeda that we can see. And if you look at this with your eyes, it would just be a very faint smudge that you could barely see. But if you have a satellite that has really good resolution, you can sort of pick out individual supergiants in the Andromeda galaxy.
So the blue light here, could you talk a little bit about what the ring structure and the blue light in the Andromeda galaxy is?
Yeah, in too much detail, like you can kind of see how I can't decide how well I can see it, and so I shouldn't. Yeah, you can kind of see a little bit that around the Andromeda galaxy, like the sky gets a little bit darker, and that's not real. That's an artifact of how we analyze these images and trying to subtract out the part of the sky that is just light from our own solar system, and that leads to some changes in the apparent color of the galaxy as you move through it. So I don't actually know why the edge of the galaxy is blue, but I doubt that's a real signal from astronomical sources. Sort of the large scale structure in these maps is not something that's very well measured. But this ring is 100% like this is a real star forming ring in Andromeda. So there's a particular ring of newer stars where stars are forming in this galaxy. And that's this pretty clear ring that you see in Andromeda.
I see.
Yeah. Any other questions?
Yeah. So not related to this image in particular. So thank you for sharing that. I can get back to the next question I had, which is like you were sharing in this case that. So you have this huge catalog of stars, and there are different properties that astronomers typically talk about. So I guess I want to start with why is it important for us to categorize stars? So you mentioned parameters, like you said, there's mass of the star, the age of the star, all these things that determine how bright it is. But why is it important for us to categorize these parameters?
Yeah, that's a good question. And it's a little bit hard. Yeah, so there's some part of astronomy which is just like, try to understand every single thing you can see, which isn't immediately the most compelling, but a big part of science is like, okay, you try to make sure you can understand everything so you can find the small number of objects that you don't understand and don't make sense, and that are really going to teach you something new about the universe. But so there's some part of we really want to understand everything. Then there are specific science cases where it's like really critical to know the detailed parameters of a particular star. So for instance, for an exoplanet science, you see there's different kinds of exoplanet science, but one way that you can find an exoplanet is they're so-called transiting exoplanets, and so there's a planet moving around a star. Every once in a while, the planet passes in front of the star, and if you're watching that star, every minute, you figure out how bright it is, how bright it is, and you see, it got a little bit fainter, and it stayed a little bit fainter for a little while, and then it got brighter again. And you keep watching it for another year and another year, and you see like, okay, every 30 days, I don't know what, it gets a little bit fainter for a little while. Then you decide like, oh, that's because there's a planet going around this star, and every time the planet goes in front of the star and blocks a little bit of its light, that's telling me that there's this planet, and now I know how deep how much fainter the star gets when the planet goes in front of it. Tells you how big the planet is relative to the star. But if you want to turn that into knowledge of like, how big is the planet actually? Is this an Earth-like planet? Is this some other kind of planet? Now you need to know how big the star is, and now you care intensely about the very details of the star, and so now you want to know the star's mass, you want to know the star's luminosity, is it in the habitable zone of that star? Now suddenly every single parameter of that star is critically important. So that's one example where we really care about the fine details of stars for a sort of hot area of modern astronomy. But there's lots of other ones. I mentioned earlier that as new generations of stars form, you've got the very early universe, the beginning of time. There's almost all the universe is hydrogen and helium, a little bit of lithium, but not very much else in the universe. Then stars start forming, and they start burning this hydrogen and helium into heavier elements, carbon, nitrogen, oxygen, the kinds of things that we are made out of. And when they die or explode, or when winds come off of those stars, then these heavier elements get blown out into the space in between the stars. And then a new star that forms from that gas now, starts life with different chemicals than that original generation of stars. And so there's like a huge effort to understand exactly how that process works. How did the first stars work relative to the subsequent generations of stars? And so, to do that kind of work, you care a huge amount about the chemical abundances of all the different stars, how those chemical abundances evolve in time, to try to understand, how galaxies evolve, how stars evolve, and eventually how things like planets evolve. Like, how did the things that were there planets around the first generations of stars? How what stars could we possibly find planets around? Do they have to be old or new? Like all those kinds of questions get tied very closely to these sort of detailed questions of how stars form and what's in them. Is that helpful?
I see. So yes, that's very helpful. So you mentioned about chemical composition of different stars. And we know that these stars are not nearby. You can't just take a piece of the star and put it in your lab, in your school or university and do some studies with it. So how are we getting this much level of detail about these things that are light years away? Where, if you take the fastest spaceship, it's going to take you 20,000 years to get to the nearest star. But we don't have that. We don't do that. So how do we get to know about these parameters, like the temperature of the star or the chemical abundance, or gravity for that matter?
Yeah, that's a good question, and exactly. So the answer that I think is easiest to give is spectroscopy, and I'll try to share my screen again to see if I can pull up some spectroscopy to get some examples of what that looks like. So if I click on spectroscopy here, no, DESI Spectra, DESI EDR, DESI DR1. Let's see if I can find some spectroscopy quickly. Yeah, exactly. Good.
So sorry, just for the audience. So DESI is the dark energy spectroscopic instrument. And then, yes, I'd like you let you carry forward, or you can add anything else to that if you want.
Yep, great. So again, this is the same viewer that I was showing earlier. So this is again a picture of the sky. Just you could think of it as just a picture of the sky from your cell phone. If your cell phone had a really fancy detector and had a huge camera on top of it, and you spent every day, every night for several years taking pictures, you would get something that looks vaguely like this. And so like this is a galaxy, and this is a star, and so this is an image, and it's full of these objects. But from this imaging, from these pictures that you could imagine having taken with your cell phone, you can see that you get a bunch of points, and they have some colors, but you don't learn very much. You certainly don't learn about how much europium is on any of these stars, or how much iron, or any of these more detailed questions. And so if you want more details about the stars, you need to take spectra of them. And so one instrument that's taking spectra of stars, and so spectroscopy is a huge effort. There's lots of different instruments that take lots of different kinds of spectra. But the project that I work the most with is one called DESI, the Dark Energy Spectroscopic Instrument, that's taking large numbers of spectra of stars and galaxies. And so this is showing some objects that DESI has taken spectra of. And so here it's taken a spectrum of a galaxy. Here it's taken a spectrum of what's called a quasar. Here it's taken a spectra of empty sky, just so it knows what things look like when there aren't any objects, so that it can compare that with locations where it does find objects that it cares about. The question focused on stars, and so I would like to find a DESI spectrum of a star. Here's a DESI spectrum of a star. So this red circle is around a star, and so if I click on this, I should be able to get a spectrum of the star. Yeah, good. So here's the spectrum of the star. And so what is a spectrum? A spectrum is morally, if you took the light from the star and you put it through a prism and it made a little rainbow on your wall, and you looked at that rainbow and you saw like, oh, this is how bright the red part of the rainbow is, this is how bright the blue part of the rainbow is, and you plotted a line of that, that's what a spectrum is. So this plot, the y-axis here is basically how bright that part of the rainbow is, and the x-axis is what part of the rainbow you're looking at. And so the low wavelength end is the blue part of the rainbow, and the red part of the long wavelength part, large wavelength, is the red part of the rainbow. And again, I can't remember what the spectral range of our eyes are, but they're roughly 500 to
400 to 700 nanometers.
700, thank you. And so your eyes cover from here 4,000 angstroms to 7,000 angstroms, and so you wouldn't actually be able to see anything out here with your eyes, and you wouldn't be able to see anything blueward of 4,000 with your eyes, but this part right here you'd be able to see with your eyes. And
so this is essentially the same thing that we do in our chemistry labs.
Yes. Yes, absolutely. And so here there's this button here that lets me smooth the spectrum, and so there's a lot of like up and down noise because we're trying to say this little tiny part of the rainbow is this bright, but it's very small, and so it gets kind of noisy. So if I turn this number up to smooth it, we can see more shapes and less noise, and you can see that there's this broad trend where the star gets brighter and brighter as you go blueward, and then it kind of turns over as you go too blue, and it gets fainter again. This has to do with the blackbody spectrum, and so if you everything that's hot emits light like a blackbody roughly, and so when you turn on your toaster oven and look at the hot orange yellow wire as your toaster oven heats up, that's because that wire is getting hot and it's emitting light, and how hot the star is or how hot the wire is determines what color it looks like. And as that wire gets hotter and hotter, the peak of the light, up here on the star, shifts, and so when it's cold, it's emitting at very long wavelengths, and as it gets hotter and hotter, the peak is shifting bluer and bluer, and so you can sort of tell how hot the star is by where this emission peaks, and that gives you the temperature of the star. And then you get also all of these sort of narrow features in the stellar spectrum, and so these are particular elements in the star that are absorbing light, or in this case, always absorbing light. And then they've got these little lines through them that are helpfully marking what transitions of what elements are doing the absorption. So like these H and K lines are particular lines of calcium that have confusing names due to historical accident. This O2 and O3 lines, these are oxygen. All of these H lines are hydrogen lines, and all of these different elements and atoms have complicated structures, and depending on how the electrons move in their electronic structure, you get different patterns in the lines. But ultimately, it's by looking at all of these lines that tells you things like how much iron does the star have, how much nitrogen does the star have, how much sulfur does the star have. And so that's how we really learn kind of the details of what a star looks like.
So essentially, chemists here on Earth, they did spectroscopy, and they figured out what the absorption lines or the emission lines for different elements are. And because these elements are the same everywhere in the universe, when we see the similar effects in light coming from stars, we conclude that this is the chemical composition for that particular star.
Yeah, absolutely. Yeah, no, it's it was definitely, I hadn't thought about this before, but for sure, when people must have been taking spectra of a lot of things on Earth, and it must have been very deeply reassuring at some level when you start taking your spectra of your first things in the sky and see, oh, I know what all these things are. We have the same stuff on Earth, and hydrogen has these lines, and I see them on these stars, and and now I know what the stars are made out of. Yeah, absolutely. We see the exact same lines in space that we see on the Earth, and that gives us confidence that we know what's going on here. I don't know. That also does remind me that like a huge surprise in astronomy was that when you looked at the spectrum of some galaxies, like this galaxy, you also found sort of the same lines that you're used to on Earth, but they were all in the wrong places. So if I'm patient, it'll pull up this spectrum, and I'll try to explain redshift for a second. But maybe I have to be too patient.
I see. I was actually going to ask if there are any sort of lines which made us think that there are other elements than the ones that we have on Earth.
Yeah, I'm not. That's a good question. I'm not aware. Okay, yeah, good. Let me talk about this one for a. Where's the Gaussian movement? Let's see if we can see a line in this object. Yeah, good. Yeah, this is a spectrum of a galaxy, and there are a bunch of lines. So here's the oxygen 2 line, the hydrogen beta, oxygen, a couple of oxygen 3 lines. So there are recognizable lines. You'll notice that this spectrum is a lot less pretty, a lot more noisy than that spectrum of the star that we showed earlier, and that's just because this is much fainter. This is a very faint object as compared with the booming bright star we saw earlier, and so there's just a lot more noise.
And that's despite the smoothing that you've applied at the bottom.
That's right. Yeah, when we started looking at this thing, it's like there's not. You still see this oxygen 2 line very clearly, but you don't see very much else. Oops, change that. And yeah, we have this O2 zoom button. Not a great oxygen 2 line, but you can see that so that the oxygen 2 line is very important for DESI because it is very recognizable as being too broad. So it's this doublet. There's 2 oxygen 2 lines that are very close to one another, and so it's easy to recognize. So often in the DESI data, you can see one peak and then another peak next to it. But in this case, I'm not seeing that clearly. It does look broader than a single line, but anyway, it's not a great example case to use. But anyway, for this, the cool thing about this galaxy is that like we've identified this oxygen 2 line, we've identified these hydrogen lines, but here it is not the case that these lines are in the same places that we would see on the Earth. They're in totally different places, and so the reason for that is that this object is at a redshift of 0.8, which means that all of the wavelengths that we see, so the wavelengths of these lines have been shifted by a factor of 1.8. And so we're still quite confident that these are the same lines that we see on Earth because they all have the same relative locations. If you take the wavelength of the oxygen 2 line divided by the wavelength of the hydrogen beta line, like all of those ratios line up exactly with what we see on Earth, but they're all just shifted. And the reason for that is that this is a really distant galaxy. The light that this galaxy emitted has been coming towards us for I don't know how long, but on the order of 1 billion years, less than 10 billion years, somewhere in that range. And the universe has expanded dramatically that time by the universe expanded in that time by a factor of 1.8, and the wavelength of the light has expanded by that same factor in that time. And so the main purpose of DESI, I was showing some stellar spectra earlier, but the main purpose of DESI is to measure redshifts for huge numbers of galaxies, because those let us measure the distances of those galaxies and map the sort of 3D structure of the universe. Anyway, you just reminded me of like it's deeply reassuring that all these lines are at the same locations that we see them on Earth, except for when they're redshifted, which is actually one of the most important things in astronomy.
I see. So this helps us. So you talked about how this helps us understand the temperature, how it helps us understand the chemical composition or metallicity. What about gravity or mass?
Mm-hmm. Yeah, exactly. The easiest thing to talk about is the chemical composition, because basically if you have more of some element, the lines associated with that element get deeper, and so that's the stellar parameter that is most straightforward to connect to the observations and what you see. So then there's the mass of the stars. The other thing you mentioned, the story there gets a little bit more complicated. So it turns out that the more massive a star is, for most of the star life, the more blue the star is, and so the most massive stars are the bluest, and so that so the mass sort of controls the temperature. and the temperature is set as easy to sort of measure, as I was showing, by where the peak of the black body spectrum is, where most of the light is coming out. And so you can kind of measure the mass of the star just from its color, where that rainbow, where that spectrum is brightest. And so that gives you the mass and the chemical abundances. And the last thing you asked about is the gravity. The gravity is another kind of measurement of the mass of the star, or a combination of the mass of the star and the radius of the star. So yeah, usually there's sort of two ways to think about what numbers determine a star. One way to think about the numbers that determine the star are the mass of the star, the age of the star, and the chemistry of the star. And as a star ages, if you have a certain mass of a star, as it ages, the size changes. And I am like sort of very early on in the star's life. It's a cloud of gas, and it contracts and settles and gets smaller and smaller. Then eventually nuclear fusion turns on in the star's core, and that fights back against gravity. So gravity's pulling the star to get smaller, but the core of the star is starting to burn, making pressure that's pushing back against further contraction of the star. And so then the star settles onto what's called the main sequence for a long part of its life, where that burning of the star's core is exactly balancing the gravitational pull of the star. That continues for a long time. So the main sequence lifetime of a star can be quite long. So the star, the sun will burn for like 10 billion years on the main sequence before leaving the main sequence. Eventually, the star burns all of the hydrogen that it can, sort of, and then gravity, can in principle start winning. But then stellar evolution gets complicated. You start burning hydrogen, helium, and shells, and then the star starts getting bigger again. It becomes a red giant, and depending on the stellar evolution gets complicated, and I'm not the biggest expert there. But the point is, after you exhaust the hydrogen in the core of the star, the size of the star can start changing dramatically. Where the hydrogen is burning starts changing dramatically, and that changes the size of the star, while leaving the mass pretty similar. And so that changes the gravity of the star, because the gravity of the star is a combination of the size of the star and the mass. So long story short, that you could think of the gravity of the star as a kind of proxy for the age. And then your question was ultimately, how do you measure this gravity of the star? And the answer is that the detailed shapes of the lines on the star gives you access to the gravity. A star with higher gravity has broader lines. And there are other ways in the detailed spectrum of the star to do this, but that's the simplest one to think about.
I see. Okay, so essentially the star, to paraphrase, when it's younger, the gravity is trying to compress it. It has a bunch of nuclear bombs that are exploding in layman terms that stop it from happening. You determine, and then for billions of years, you're going to get that light, which is typical of stars at that age. And we know about that. We know about gravity being related to
That particular signature of light. Is that
the correct summary.
Yeah, I think that's right. Yeah, the nuclear bombs is of course colloquial, but is not wrong. It's more like what something like ITER, or the nuclear fusion power plants that don't exist yet, but people are constantly working on, where you're imagining trying to take a nuclear explosion, but spread it out very gradually, so it's not all going off at once, and so is a steady nuclear burn instead of a brief uncontrolled nuclear reaction. But yeah, it's ultimately taking hydrogen and fusing it and releasing a lot of energy over a long time.
I see. And so I have one last question. So could you talk a little bit about any upcoming missions or technologies that would help us understand these stellar parameters or would help improve the understanding of stars?
Yeah, sure. The mission that I'm most involved in right now. So we talked a little bit earlier about DESI, so the Dark Energy Spectroscopic Instrument that's doing spectra of huge numbers of stars. So maybe I won't talk about that one again, but that's that's one interesting project that's doing a lot of stellar spectroscopy. The other mission that I'm involved in is called the Nancy Grace Roman Space Telescope, and so Roman is an upcoming telescope that is kind of like Hubble. So the main mirror on Roman is the same size as the main mirror on Hubble, but the big difference with respect to Hubble is that the so-called field of view of Roman is 100 times larger than the field of view of Roman. I said that wrong. The field of view of Roman is 100 times larger than the field of view of Hubble. So basically, you can think of every picture that Roman takes as being, 100 pictures that Hubble would have taken. And it's even more than that. Like the Roman detectors are newer. It's an extremely stable platform. It has lower overhead. So by some metrics, Roman observes the sky 1,000 times faster than Hubble. But so that's a instrument that I'm very much involved in right now. So I'm working on the Roman calibration pipeline, so the software that's going to turn the observations that Roman makes into calibrated images, and eventually lists of we found a star here. This is how bright it is. That people are going to turn into a lot of science telling us what the galaxy looks like. In particular, one of the projects with Roman that I'm working on is known as the Roman Galactic Plane Survey. So that's going to be 700 hours of Roman time spent observing the galactic plane, so the part of the sky where most of the stars are. We've done some simulations for what Roman is going to find in that galactic plane survey, and some of those simulations have predicted that we could find up to 100 billion stars in the Milky Way. That's a crazy number. Yeah, that connects to the number that we were talking about at the beginning, like how many stars are there? Like Roman is good enough that we will see a substantial fraction of all of the stars in the Milky Way. Literally being able to count each one rather than estimate broadly how many stars there are. That's going to provide a huge amount of information about the structure of our galaxy, where star formation is happening, how star formation proceeds, where the dust in the galaxy is. So lots of questions about how the galaxy works, how the galaxy evolves, what the galaxy looks like. So yeah, that's a major project that I'm working on that's going to give a lot of cool science.
That's very interesting. And if somebody wants to access all this cool and interesting research that you're doing,
is there a place where they can go and check out your work?
Sure. I have my own personal stuff. I have a little website. e.schlaf.ly for my last name, my first initial and my last name, where I put links to some of the stuff that I'm working on. Astronomy in general is basically all papers are posted to the archive, which is a sort of public, totally free, if you want to read papers in astronomy, you can read every paper in astronomy that's published as it's published, before it's published on the archive. So that astronomy is very, very open about all of its publications, and even not just the publications, but the data itself. So all of the Roman data is going to be public. So if you're very excited, you can go to the Roman website. So Roman hasn't been launched yet. There's no Roman data yet, but You will be able to go to the Roman website and download all of the Roman images and look at them and do science with them. And so there's been an increasing trend in astronomy to make sure that all the publications are public, the underlying data is public. Everything is pretty fully reproducible.
Yeah, and actually the Roman Space Telescope, the website that you're talking about, I'll add a link for that in the description, but it says it's a NASA observatory designed to settle essential questions in the areas of dark energy, exoplanets, and infrared astrophysics, which sounds pretty cool. And maybe we could talk about that another time.
Yeah, sure. Yeah, I talked about the stellar, component of Roman's mission, but exactly the reason that Roman has been launched is not to do the stellar science; it's to answer a lot of fundamental questions about the universe. So the stars that I was talking about a second ago are tens of kiloparsecs away, so 30,000 light years. But most of the objects that Roman is going to look at, most of the time that Roman is going to spend doing observations are focused on galaxies that are billions of light years away.
Okay, sounds good. Thank you for your time, and I hope you do this again.
Yeah, great. Thank you, sir.